So the light will turn red.
Which will be an hour past the schedule open. Is everybody clear on that? Okay. Closer. All right, we are ready now. The first talk of the afternoon is Benjamin Hinrichs from Paderborn, who will talk about the ultraviolet renormalization problem.
Thank you for the introduction, Jakob. Yes, thanks to the organizers for organizing this very nice conference here in Mexico, for the opportunity to spend a few days in Mexico, for the very nice excursion today, and for the possibility to speak here at this very nice conference at the occasion of Volker's birthday. Today I want to talk about very recent joint work with Marco Falconi from Milan and my PhD student Javier Valentin Martin about the ultraviolet problem. And I thought, as we are at the Museum of Light, it's good to speak about something with light. So I'm going to talk about the ultraviolet problem for light-matter interactions. Let us jump directly in and briefly talk about what do I mean by light-matter interactions. So I mean sort of that we have given some type of quantum system called matter or particles, which interacts with the quantum field, which we think of in this talk as photons, but neglecting spin degrees of freedom, or like any degrees of freedom, we'll have them spinless. And I mean, the interaction is basically, okay, you have some type of energy levels, continuous spectrum, discrete spectrum of the particle, and the particle can absorb or emit photons to gain or lose energy. So basically, we're talking about Hamiltonians of this type. We've seen something similar in the previous talk by David Hasler. And then maybe a disclaimer, when I talk about renormalization, I don't mean the same renormalization. David was talking about the infrared problem. I'm concerned with the ultraviolet problem. So it's completely different techniques and completely different statements. Okay, so sort of this type of Hamiltonian consists of three parts, similar to the last talk. Nevertheless, there's sort of a matter Hamiltonian really describes energy levels of the matter or particle. Then there's a field Hamiltonian, which describes sort of what the energy of the field is. And then there's some type of interaction. And I will discuss these types of models with respect to two parameters, or in the end, more or less only one. The one basic is sort of the dispersion relation of the photons, which is this function omega. which I want you throughout this talk, and I'll later on stick to this example, really think of as the relativistic dispersion relation of massive or massless photons. Okay? I mean, usually, I mean, of course, especially in the infrared problem, we think of massless photons. Everything I'm going to state holds for massless photons, but there's slight technical difficulties. So I will later on fix the mass to be one. But it's not really for purposes that the statements don't hold. It's because I don't want to bother you with technical details, how to treat massless case. And what is for us going to be the important function, which is why I put it as an argument into the Hamiltonian, is the interaction potential or form factor, often called form factor in the literature, which sort of describes what is the energy needed to create a photon of momentum k, or vice versa. What energy does my system gain when I absorb the photon of momentum k? And for the physical light, as we want to discuss light matter interactions, it's supposed to be 1 over the square root of omega times some real component. We'll think about sort of these choices of parameters throughout the time. These models are of large interest in general in the mathematical physics community, but also to many people in this room. So I listed a few people. It's a far from complete list of a few people who worked on, say, spectral and scattering analysis of this type of models. And if you look closer, and there's quite a few, the red is not good to see, but there's quite a few people in this room here who have worked on the problem. I would say at least a third, maybe even half of the speakers listed, organizers list of the conference. So I think it's the right place to talk about this. I'm nevertheless not going to speak about spectral or scattering analysis. I want to talk about the ultraviolet problem. So what exactly does it mean? It's a very basic problem. It's maybe the first you want to ask if you say, okay, I want to study this type of Hamiltonian. It's the question, can I define this Hamiltonian? And broken down, maybe not fully rigorous, but broken down, it's more or less that we don't really know what to do if this interaction fails to be a perturbation in the operator or form sense of the free Hamiltonian. So sort of, we get into trouble with the well-definedness of the Hamiltonian if that is the case. So that is sort of what I mean by the ultraviolet problem here. And we can also characterize pretty precisely what it means to have at least a form perturbation of h of 0. If you add, let's say, the dispersion relation of the particles, so say you know how this particles behaves to the system, then it is explicitly characterized by sort of the square integrability of this ratio. So if you take the interaction potential, you divide it by the dispersion, by the square root of the dispersion of the photons, and okay, you can add the dispersion of the particle, if you like, which helps you if you have a non-relativistic particle, because then this sort of increases faster as k goes to infinity as to omega. And then sort of if this function is a square integrable function, then sort of beyond the range of form perturbations where everything is supposed to be nice. And if you want to make it general with this assumption, then that is basically a commutator result by Yamazaki. But now I said, I want you to have these functions in mind. You can insert these functions in 3 dimensions into this assumption, and you'll see it doesn't. So we are definitely outside of the range, and maybe with one exemption. No. We are definitely outside the range. So this assumption, even if we choose omega of k to be 1/2 absolute value of k squared. So even if I add a non-relativistic particle, then I'll still have an ultraviolet problem. I won't have a form perturbation. I'll have some. So we definitely have to find a solution. And I want to talk a little bit about, well, first about older solutions to the problem called self-energy renormalizations, and I'll discuss their limitations for physical models, and especially I'll discuss 2 models which do not have a self-energy renormalization, which is closely related to the problem of triviality. And then I will discuss 2 recent papers joined with Marco Falconi, and the second one also with my PhD student, first on the Van model, and then on the spin-boson model, in which we propose the renormalization scheme, which overcomes this triviality problem. It sort of provides an ultraviolet normalized model of this type, even when in exactly this physical case and in more critical cases. So go beyond the criticality, if you like. See that later on. But let's start maybe with the older known results on self-renormalization. And as a very short intermezzo, but we've seen basically everything on the slide already today and also in previous talks. Let's discuss what the example models are and how they are mathematically well defined. Well, we use a bosonic Fock space field. So it's given by, I now free the space dimensions, so take d dimensions. The n particle subspace will just be the symmetrized square integrable functions with d times n variables, symmetrized the number of RD variables. And the two types of operators we want to introduce are the free field, which I now denote by second quantization notation with d gamma of omega, given exactly as in David's slide in the last talk, by summing over all the dispersions of the photons and adding them up. And as another basic instrument in this talk, I want to see the annihilation operator for now with purely regular form factors. So you take a Hilbert space element and you annihilate a particle which has this Hilbert space element sort of as its momentum distribution, and that is just given by, okay, you integrate out the complex conjugate of v of k against your symmetrist function. And okay, you scale it appropriately so that this operator and its well-defined adjoint, they satisfy the canonical commutation functions. And the type of Hamiltonian basically looks the same as we had on the last slide. The only things I changed is, okay, this HF, this is now the second quantization operator. And I'll ask for my interaction to be linear in A and A star. So I'll only treat linear dimensions. And the typical physical examples I want you to have in mind, or which I will discuss in this section on self-energy renormalization, are the spin boson model, in which the matter space is just the two-dimensional Hilbert space C2, and the matter Hamiltonian is just the diagonalized third Pauli matrix. We have the energy levels 1 and -1. And the interaction is given by absorbing or emitting photon of form factor V, and the spin changing. Sort of you flip from -1 to +1 or vice versa, annihilate or create it. It's a very common model, especially if you study optics, but also to study effects like you can use the spin as an approximation of matter in the so-called Wigner-Weiss formalism. And another class of important models are the ones introduced by Nelson, and then generalizations using other dispersions, in which you really use for the matter space the L2 space over RD, and you give the particle dispersion relation large omega, as I had on the last slide. So sort of this is the energy of the particle. And then the interaction is given by annihilating or creating a particle at position x, where x is the variable with respect to which I differentiate this operator. And sort of this is just given by Fourier transform, essentially the interaction. So these are the models I want to have you in mind for this introduction. And then we can ask for simple or classical solutions in the sense of the self-energy renormalization of these models. And as I said, I will, up to now, from now on, start only discussing photons of this one. And this is just the same as before. This is exactly the operator describe. And the ultraviolet problem translates, as we have already said in the introduction, into, okay, the operator self-adjoint and lower bounded if we can assume this form perturbation assumption, sort of the field or this interaction of V that is really a form perturbation. And if this is not the case, if I give you an interaction potential which does not satisfy this integrability. So, I mean, this doesn't look like an integrability assumption anymore, but it's really only a domain of an operator in L2. So you can also think about it as V and V over square root of omega are both square integral functions. And if these are not satisfied, if you want to have an interaction potential which does not satisfy this assumption, well, then you can try to do a self-energy renormalization. So you can basically cut off your interaction at the moment n, that is sort of an ultraviolet cutoff, which ensures that I'm in the range of this integrability assumption. Then you can take your well-defined self-adjoint lower bounded Hamiltonian, subtract the ground state energy, and ask, does this thing converge in an appropriate sense? And that's what I would call the self-energy renormalization. You only take away the diverging ground state energy, and then you get a well-defined. It's not a coincidence that I discussed this in the context of the Nelson model, because that was basically the first rigorous result of such self-energy renormalizations in Nelson's original paper, 64, where he discussed the three-dimensional Nelson model, in which the matter particle is really a non-relativistic particle, non-relativistic dispersion. And he was able to prove that actually you have an explicit constant which behaves at infinity like the ground state energy. You can construct a normalized Hamiltonian. This also works if you take relativistic particles, but only in dimensions 2. That's a result by Sloan in 1974. And you will get into trouble if you try to treat the Nelson model with a relativistic particle dimension 3. The conjecture is that there's no self-energy normalization. I don't think there's full rigorous proof, but definitely there's a result by Alessandro and Dirk Deckert saying that if you find a self-energy normalization of this model and you look at the ground state energy, at least in the translation case, you will have a flat mass shell, which essentially indicates that the particle and the field have decoupled and you only have a free field. Correct me if I'm wrong. And not only for the Nelson model can we sort of study this problem, we can also look at sort of the spin-boson model. And there one can explicitly distinguish when the self-energy renormalization is possible or when not. You can really give an integrability condition on the interaction potential, which replaces this 1/2 by a 1. And if you have this integrability condition, you'll be in the range of self-energy renormalization. And if not, you'll really run into a triviality problem, which I will briefly discuss later on. So far, maybe to the results. And what I want to do in this talk is really, I want to address the cases which land in this category. You sort of have triviality. You cannot self-energy normalize the model. Somehow in the original Fock space, you will not get a limiting operator if you try this type of procedure. And well, basically you end up with a free field. So if there would be a renormalization, you end up with a free field, even if you sort of, I'll say it briefly in a second when I discuss Nelson's dressing, but even if you go to a representation in different Hilbert space. And everything is based, and we'll compare our method to that on dressing transformations, which is actually the idea that Nelson originally used in this paper in 1964. So what you basically do is you don't look at the operator itself, you transfer it into an, in the regular case, equivalent system or equivalent Fock space in which you have already incorporated the photon cloud into the states. That's what one calls a dressing transformation. And the dressing transformation here takes this form with respect to creation and relation operators. And then if you sort of apply this dressing transformation with the right scaling, and here you already see this ratio, which I want to be square integrable if I want a self-energy renormalization, and I want to leave L2 if I want to run into the triviality problem. If you do this transformation, then you will get something which is more regular in some sense. We'll see it for the spin-boson model later on, but it also holds for the Nelson model, minus an explicit self-energy. So that's sort of the concept behind these dressing type renormalizations, that by applying a dressing transformation, you can sort of get something which looks nicer, which you can directly construct. You can directly construct this operator after taking the limit n towards infinity. And then you can use these unitaries to go back. And this going back is sort of the important ingredient why we need that this ratio also stays square integrable in the limit if we want to have a self-energy renormalization. Otherwise, the two representations will be detached from each other. They won't be equivalent. You cannot go from the one to the other. And what I mean by triviality is if you transform the model and then take the limit, the regularized model in the limit that you want to construct, that is the triviality coupled. That's sort of the triviality type. So sort of even if you go to a non-Fock representation, what you get in that representation doesn't satisfy the properties of the physical model study. Okay. And so apparently, or I'm claiming these results indicate that this is essentially, if you want a non-trivial model, the wrong dressing transformation. I will discuss what properties the right dressing transformation should have, and then suggest an explicit one, test it on spin-boson model. But before we come to the spin-boson model, let's come to a more simple model, which is exactly solvable and which is therefore the perfect testing ground if you want to do a different method. It's the Van Hover model. And everything I'm going to say here is in this preprint, which is in a proceedings article here in May on arXiv. And okay, what is the Van Hover model? It's essentially also a model of the form, but you make the matter trivial. So the matter has 0 as a Hamiltonian and the space is just C, so the tensоrization gives you nothing. It's really just an operator on Fock space given by free Hamiltonian plus field A, say star. And this model is exactly solvable. It's diagonalizable, and you can do it by exactly the unitaries we just saw. And what you will get is the free field plus the self-energy term we also just saw. So sort of this is actually nothing new, but in the Van Hove case, the regularized model is just the free field. And that's why the model is, in a sense, inherently trivial, because sort of you really have the free field as the Racine transformed version. And because you have that, what I discussed on the last slide, that, okay, I can now take, if I want to enter a sequence here, take the limit and then go back. This unitarity of the transformations is, of course, important because it allows me to take the free field back in the Fock space. So you can summarize this in a renormalization result like this. It's definitely written down in Dzerzhinsky. It's probably older. That sort of, if you have a sequence in which you have regular form factors, if you want this thing to converge in an appropriate sense, you need this ratio V over omega to be squared. Otherwise, it won't work. And of course, you have, or nevertheless, you do have a representation in which you can perfectly take the limit. You can just stay on the right side after summing the self-energy. You can just look at this thing. This is a constant sequence if I insert any V. So definitely, there is a non-Fock renormalized operator. It just occurs if you take this limit. It's the free field. Okay, it's trivial, and you can't say anything much anymore about physics. So somehow, okay, I can construct a non-Fock renormalized operator, but I lost my information about physics. So what I want to do is I want to regain the information in the case that this V over, that this condition is not set. Yes. It's the non-Fock space, but it's of course not the original Fock space. So for non-Fock in the sense of I change representations of the CCR and I can't. Of course, it's still a Fock space. Any other questions? Yes. You're going to see it in a second. Yes, and that's exactly what we're going to do. Yes, we're going to see exactly like that. We're going to subtract the energy and we're going to rescale this. So it is what we are going to end up is a type of wave function. What I want to motivate it with is a C-star algebraic motivation model, because what we are going to end up with is exactly what you get if you would try an algebraic version of generalization. Okay, so what does C-star algebraic formulation mean? Okay, we take the Weil algebra or CCR algebra. Thanks for Volker for already talking a little bit about C-star algebras. So because obviously creation and annihilation for bosons are unbounded, we take the exponentials and we look at the Weil algebra of the CCR. And we'll actually not look at the full algebra, we'll look at sub-algebras generated by some subspace. So I'm going to use this notation W of D for the Weil algebra generated by Weil operators, which I insert some more regular function than O2. Okay, think of this as some nice test function space. I'll specify it in a second. And well, then if I go on the standard Fock space, there's a canonical representation for it. It's just the exponential of the field operator. So this is nothing else, and this is why it's called CCR algebra, because the generator is again the field. And so this is sort of the representation on the original space our model lived. And then I can define the Van Hove model by its generating maps on the level of the C-star algebra, and explicitly just by explicitly incorporating the unitary dynamics of the Van Hove model on this standard representation. Okay, so in the standard representation, I take the unitary dynamics of the Van Hove model, and I can calculate these because it's exactly solvable. We know what diagonalizes the model. We can just calculate what comes up by using the Weil algebra and what we know about the diagonalization of the Van Hove model. Okay, so we get sort of an algebraic version of the Van Hove model as a dynamical map on the Weil algebra for an appropriately large subspace. More than that, we can also calculate what the ground state of this model looks like. Right? I mean, if I go to the standard representation, I think there's a pi 0 here missing. So this is the standard representation. Then I can diagonalize with these unitaries we saw before, acting on the vacuum, acting on the ground state of the free field. And I can calculate what comes out. Function. And I can call this now the algebraic ground state of the model. And it actually satisfies ground state properties, appropriate algebraic states. So how can I solve the ultraviolet problem for this? Well, I need to look if I can find an appropriate definition of the right-hand side of this expression and of this. If I can do that, I have on an algebraic level solved the ultraviolet problem. And I can do that. And the setting which we'll use throughout this talk is the following. We take a set of test functions for our Weil algebra, which are regular. Let's say compactly supported functions, and we equip it with the usually the standard locally convex distribution from distribution. Then we take the associated distribution space. This will be the space in which our form factors. Okay, so these are, I can basically take any distributional form factor. That's like any interaction potential which comes from this topological anti-dual space. Anti-dual because I want to have scalar product generated, but I want to embed my complex Newton space. And then one can easily see that if you take the compactly supported smooth functions and omega is square root of 1 plus k squared, then 1 over omega is just a continuous operator on this space. And thus, by duality, it also has a transpose dual space. So 1 over omega is a perfectly well-defined operator on the distribution space. And I can, as usual in this theory of distributions, I'll use the dual pairing of d and t prime to denote scalar products, which immediately also gives me an embedding of L2. Okay, so any L2 form factor will, of course, be embedded in d prime and will be a superset of the compactly smooth. So somehow we have this nice dual pairing, and I'll use it. I will not care throughout this talk if this is an L2 or if it's distribution. But with this dual pairing, I can just look at the expressions on the right-hand side, and they immediately make sense. V is a distribution. Maybe look at the ground state first. V is a distribution. 1 over omega is a continuous function, so this is still an element of d prime. Of course, I can take the scalar product, the dual pairing, with an element of d. That's a well-defined expression. I can use it. Same holds up here. This is a continuous operator. This is also a continuous operator. This is the dual pairing. And this is just the standard free dynamics generated by omega on d, on L2. So both of these things make sense. I have an algebra. I have a ground state. I can do a GNS construction, and that's, I would call, the correct physical model to study. So sort of, and what you get if you do an appropriate construction, you can find details, for example, in the book of I, that you'll just get a new Fock representation in which actually the generator of these dynamics is just the free field. And this ground state corresponds to the vacuum. So somehow, even if you do this renormalization on an algebraic level, which seems to be extremely natural, you'll end up with a trivial model, which tells us somehow Fraunhofer is very trivial. It's inherently trivial, yes. It's exactly so. You can take any distribution. But I mean, sort of, yeah, but nevertheless, you can sort of start with the V, and then, I mean, these expressions still make sense. The space is large enough to generate massive space. I'm not sure I see the point of the question. Yeah, I mean, you can really take any, I mean, you want to do it more abstract, you can take any test function space with a nice enough topology, which is finer than L2, and then the dual space will give you, you mean the form factor? Yeah, but I mean, that's an element of d prime. So you can take the light form factor, you can take constant function, you can take delta, anything will work. And all on this space. As long as you keep the mass, if you remove the mass, you need to change d a little. But you can take d smaller and then we'll still. So the mass is not a. Okay. If you would take this approach, go to the spin-Boson model, things would get complicated because we don't have the diagonalization, the dynamical map is going to get hard. So what I want is an analytic construction of this GNS representation. I want to do a dressing transformation, which is non-unitary in the style of Nelson, which gives me exactly this representation in a natural way. And so that's sort of the goal of what I want to do for the Fraunhofer model and the transfer to spin-Boson. So I want to do ultraviolet renormalization by non-unitary regress. And the strategy actually comes from two papers from the 70s. We found, or we especially looked at this paper by Genibre and Velo. They treat an exactly solvable quadratic model field. And they motivate their work with an older paper of Grimm on the I think, Yukawa model in 2 dimensions. And the non-unitary dressing transformations rather similar to what we saw with Nelson. The only thing is we drop the annihilators from say the exponent, and we sort of only dress with a creator and then do a master normalization by scaling with the vacuum. So sort of we dress with this creator and rescale with the vacuum normalization. And if you only look at the vacuum sector, this will have the same effect. So the vacuum sector will actually look like in the original Weil dressing. But of course, we're excited for other states. Okay, so that's the dressing we want to apply. And we want to sort of compare to the algebraic approach I just showed. And okay, but what I need is sort of, I'll need a appropriate space of Fock test states now, but this is easy. It's just a finite particle subspace over our test functions, which basically means, okay, I take these symmetrize that there should be an S here, tensor product of n of these regular test functions, and then I take this, the finite particle subspace over our test function space. That's a subspace of Fock space. It's dense. It's nice enough to test anything which we want. And then I make the second observation that, of course, I can never create a distributional particle, because if I want to try to create a distributional particle, well, then I'll create something which I cannot describe. But what I can do is I can annihilate distributions. That's not a problem at all. I mean, it just means taking scalar products. So the expression we had as a definition of an annihilator immediately translates on this state of test states to a definition of an annihilator which takes arguments in the distributions, but only acts also states. Makes perfect sense. And it's even sort of, you can apply it arbitrarily many times, because if you annihilate often enough, you'll just end up in the vacuum, and after that in zero. So sort of, this is not only well defined, you can also take arbitrary powers of this test space, which is important for us, because what we want to do is we want to now dress with this creator for regular form factors, right? So this is not defined for distributional arguments, but it's sort of the calculation we actually need to do. We want to dress our states with the exponentials of creator. And then it's a simple calculation using the CCR. We take this, this e to the a star, we take it to the other side, it becomes an e to the a, and then I have to commute e to the a and e to the a star. That's the Becker-Campbell-Hausdorff formula. And that will give you a commutator of a and a star. And if you wonder why the 1/2 from Becker-Campbell-Hausdorff is missing, well, I need to take 2 of those, because I don't want to write the sum in the exponential. I want to change the exponentials. That's why there's no 1/2. Okay? And then I pull the a star, I pull to the left to the other side, and I get this scalar product. And then I look closely at the exponential I got from Campbell-Hausdorff. That is exactly the square of my scaling. Essentially the same calculation gives me that this is the norm with which I want to regularize. So the ratio I take will just put this to 1. And what remains is this scalar product. And this is the scalar product in what we now call the dress tilt space. So what we get is the finite particle subspace over D, sort of the test space we took, equipped with this scalar product. That is a pre-Hilbert space. And then I can take the completion. That will be the Hilbert space I want my model to live in, the dressed Hilbert space of the Van Hove model. Yeah, and we can construct it for arbitrary distribution of G. Of course, they'll differ. Scalar product depends on the G, heavily depends on the G. Okay, and then I can do the same with the Hamiltonian. Now we just have a scalar product. Now I want to dress the Hamiltonian. I'll do the same thing. It's a little bit more complicated. It's maybe say 5 steps in between, but it's nothing else. It's a calculation using CCR. I take my regular form factors to the left and to the right, and then in the creators, I pull this over. I commute first with H, and then with this. Then I put everything else to the other side, and it will look very related to what you get if you use the unitary dressing by Weil transformation. So you'll get the factor with which we scale from the Becker-Campbell-Hausdorff formula, and your interaction term will drop out by commuting with these exponentials. Remain with a free field and a self-effect. Now, I know that I rescale this away. That's just by my wave function normalization. And this is a quadratic form, which if I sum the self-energy, if I take away the self-energy, will converge to a perfectly well-defined expression. It's these e to the a's, which are well-defined on our test function space, and they sandwich a d gamma of omega, which I can evaluate. For example, in the sense of quadratic forms, which would be the method by Geneva and Weber. So it gives me the Van Hofer model on its dressed Hilbert space as the model on its dressed Hilbert space. For example, by taking this quadratic form and then proving, well, that it's closed, bounded from below, symmetric, then you get a self-adjoint operator. And you can even prove more. You can prove that this operator HG is essentially self-adjoint on the finite part. Okay, so it's the unique operator that comes from this quadratic form on the space FG. That's what this says. There's a unique self-adjoint operator, the dressed Van Hofer model on our constructed space FG, which corresponds to this quadratic form. And now you ask about non-Fock. And actually, you can go back to Fock space, but of course, again, it will be in a completely different representation. It will not be attached directly to the CCR, but it will be the GNS representation. And the embedding is very simple. I just take this map E to the A of G, which maps my finite particle subspace to itself. I'm sorry, this should of course be a D, not a T. And this map uniquely extends to a unitary from FG into the original bosonic Fock space, in which the operator HG becomes the free field. And this is exactly, you can prove there's a natural way to equip it with the Weil representation, that this is the GNS representation of the model. So this type of dressing, this procedure, is actually a natural way to construct ultraviolet normalized Hamiltonians for arbitrary distributions. And it immediately also gives you a renormalization scheme just by sort of inserting regularized form factors in your model, which converge to the distribution you want to have as a form factor in the weak star sense. And then you will get that the dressed and rescaled quadratic form of the spin boson model converges exactly to this Hamiltonian if I choose the dressing similar to Nelson, like exactly in the way that it cancels the interactions we can. Right, so sort of you can, if you see a G in this talk, you can always think of the G as a V over omega. And I just didn't want to write V over omega. But I mean, in the sense, sort of that's the relation between V and G. It's a 1 over omega. Okay. So that's the renormalization scheme we want to use. It works very well for Van Hofer, but in the end, it's still trivial. And the title of my talk said something about non-trivial. So maybe we should go to something that's not so trivial. So let's go to the next class of models we want to treat with this renormalization scheme. And it's a spin boson model, for which we already know that there is a regime in which self-energy renormalization will not work, thanks to Jakob. It's one of PhD students. It's done. And maybe let me first briefly remember you of the Hamiltonian. So what we said is the Hilbert space of the model is now C2 tensorized with the bosonic Fock space. So we take 2 degrees of freedom in the matter, the particle. We take the diagonal sigma set as the energy of the spin. We add the free field, and the interaction is given by free spin. Okay, and in the end, we again want V to be a distribution, and the A stars to somehow go away. But of course, to have this well defined, I'll need Vn again to be in the domain of the sum. And if you want to do a self-energy renormalization, that's essentially what I meant on the slide where I had this table, is that, okay, similar to the Van Hofer model, self-energy renormalization can only exist if this ratio is held. Otherwise, you're lost. You're definitely not going to do anything on the original Fock space. It's just not possible. And what Jakob and Thomas actually also proved is that if you do the unitary transformation with Miles, and you take this limit, then you again end up with a free field not coupled to the spin. So actually, it has exactly the same problem as the Van Hofer model. In the end, you're still going to be trivial, and you're not going to know the physics. So what we want to do is we want to know the physics. It's these models, Wigner-Weisskopf atoms, they are in physics models, so it would be nice to know how to describe them without cutoffs. And the idea is similar to before. The only thing that changed is we have the interaction with the spin in the exponential. That's the only thing that's different from the expression before. We have the same scaling, we have the same creator, but we add a sigma x. And the first observation is half of this Hamiltonian is exactly the same as before. Doesn't matter if I treat the Van Hofer model matrix valued or only on Fock space. Okay, so this sigma x, this should be an A plus A star, but I hope phi is A plus A star. And if I only use this part of the interaction, so if I first neglect the spin, then you can do exactly the same we did. You will get a new scalar product, you will get a new Hilbert space, you will get a new, this quadratic form will give you a self-adjoint Van Hofer type matrix valued Hamiltonian on your dressed space. So we don't care about these terms. What somehow needs We'll come back to them and see that we do care a little, but I'll discuss that later. But what we should discuss is what happens with sigma. And well, that is basically what does this scalar product turn into if I use my CCR, right? These are the dressing transformations. There's a scaling, but I'll not write it for now, and I put a sigma set in it. Well, and if I have these two matrices, I can do something very simple. I will decompose spin part of my vector psi into the two eigenstates of the exponential of sigma x. So I'll take these vectors plus and minus. They are just the eigenvectors to the values +1 and -1 of sigma x. Essentially, I diagonalize my normal operator. Do that. Okay, and then I now not test on the full f finite of D tensorized of C2 space. I only test on pure tensors. That allows me to say, okay, this is like a Fock test state. This V and W, they are just C2 vectors. So I can really decompose V and W into their components with respect to plus and minus, which is what I've done. This is really the decomposition into the plus and minus components of V and W. And well, what happens if I do that? If the e to the sigma xa dagger acts on I tensor psi, well, then here the eigenvalue will appear, right? I mean, sort of sigma x only acts as the eigenvalue r, and on the other side the same. So why is that important? Well, these things are non-commutative. I can't just pull the e to the sigma xa star through, but I can as soon as I have decomposed and turned it into scalars. Now I can pull it through because this is only a Fock space vector. This scalar product, this is a tensor product. This is something which only acts on Fock space, so I can decompose it into the product of the two scalar products I have, which is, okay, I have the matrix element with respect to the eigenspace of sigma x, not of sigma z. That's important. That is the non-commutativity, right? This is sort of the non-commutative behavior. And this is sort of what I end up with on Fock space. So this is a Fock space scalar product. This is a C2 scale. And then I do the same as before. I do CCR, I pull it to the other side, Baker-Campbell-Hausdorff formula, and I end up with this. And okay, I did two steps. This thing lets me end up with this. The J and I exchange places, and I only have annihilators left. And this thing is, well, it's the behavior of sigma z with respect to the eigenvectors of sigma x, but they two anti-commute. So sigma z takes plus to minus and minus to plus, which means this is a delta ij. The opposite, 1 minus delta ij. It can only be 1 if the two are different. So I reduce the summons to those summons where I and j are not the same because of the anti-commutativity of sigma x and sigma z. This is the same thing as before, and this is e to the ij times the scalar product from Baker-Campbell-Hausdorff. Okay, but now if I look at this closely, I and j are different values of +1 and -1. This will always be -1. It's a scaling factor of e to the minus norm t squared. And then we scale once. This becomes an e to the -2 norm t squared. If I go into the supercritical setting, this thing will vanish. Nothing remains. This periodic form will go to 0. Okay. So summarizing, similar to the theorem about the Van Hove model, what happens in the standard spin boson model of sigma z and sigma x, take a distribution, the form factor, take the test function space, algebraic tensor product with, this should be C2, I'm sorry, this should be C2, so pure tensors and their span. Equip it with this new scalar product, it becomes a pre-Hilbert space. You get a unitary embedding into the original space. Everything is the same as the Van Hove model, same calculations. And if you go into the range of supercritical interactions and you define, if you now have this embedding in the free Fock space, you define sort of this free field conjugated with this unitary embedding, then the scalar product rescaled, sort of this new dressed Hamiltonian in the renormalization scheme will, there's phi missing, but sort of will be the scalar, the quadratic form associated with this operator Hg. Okay. The natural question is, I have used the free field to construct this operator. This looks very trivial, and I claimed I'm going to show you non-trivial. But after all, it's not trivial. The first observation is basically my answer to what I said to you. These CCR representations are very inequal. So sort of this model on our space Fg is not an uncoupled model. And we can actually, in the case of the spin boson model, make that explicit by calculating how this quadratic form looks on pure tensors. And it is coupled because of this exponent sigma x. It acts different on different sectors. So that is non-trivial. The sectors are interacting through a even through a free field. Right? This is not e to the a as in the Van Hover model. It's e to the sigma x, which gives me an interaction of the spin, non-trivial version of the spin boson. And you can explicitly write the quadratic form on pure tensors by doing the decomposition we did on the last slide. Next natural question would be, if I take like another model of, say, a two-state quantum system, I change sigma x or change sigma z. Will the free spin, will the rest free spin always be zero? Or can something else? I mean, we did this calculation and we saw, okay, this thing goes to zero. Will that always happen if I add an arbitrary matrix? And of course, yeah, yes. Yes. We don't know. That's future. We will. We want to, but we have not. I mean, that's the next step. This is sort of the construction of the model, and the next step is exactly that. You're going to see it on the last slide with summary and outlook. I'm going to say spectra together. But you need to prove it with dynamics. Absolutely, I agree. But that's exactly the next. But for now, I want to convince you that even if we would see that this specific model becomes trivial, there's similar models which are definitely not trivial. So even if you still say, and it's absolutely legitimate, that this still looks trivial to you, then I'll show you things which are not trivial. The first thing will be, okay, does the dress-free spin part converge to zero? And there's a very simple example in which this does not hold. As soon as I drop the non-commutativity, let's make it commutative. Let's make it identical. What will happen is I will get here just factor 1, which means here we will get exactly the e to the norm g squared that we always had for scaling. So this scalar product will remain. It interchanges the sectors of sigma x inherently. And this is not a scalar product with sigma z. It's something different. It somehow interchanges. So yes. I replaced sigma z with sigma x. No, I went back. I'm sorry. This is just, I went back to the slide to say, okay, this matrix element is not the same as before. It's now identity or delta I. Sorry, that was confusing. But yeah, so if I put sigma z and sigma x the same, I'll essentially get something like this. So you could maybe still say it's trivial because, I mean, you have coupled model and then you put this strange transformation on. I would claim this is definitely not trivial anymore because this thing interchanges the sectors of sigma x. So there's sort of some inherent, this is really a fully intact, right down on the finite variable subspace. But we can go even further. I can give you a model which is still closely related, in which you cannot decompose into representation. And for that, you need to go to, let's say, arbitrary bounded systems and dress the field. That's the so-called generalized spin boson. We take two bounded operators, A is self-adjoint, B is normal, so that we can somehow do an eigenvalue decomposition. We take the same model as before, only replacing sigma z with A, replacing sigma x with B and B star. And I apply the same dressing transformation as before. I take sort of the creation part and I regularize with something with a sort the creation part, but you will now need to treat that this is an arbitrary element. So you need sort of this B star B. This is not just a constant, but it's something closely related. Yep. No, I mean, S is an arbitrary Hilbert space. S is an arbitrary self-adjoint operator. You can insert the self-adjoint operator if you like. You can insert, but no, it's definitely not because in the rotating wave approximation is nilpotent. So this is something that you cannot add. That's different. I don't know what to do. I need the normality. And why do I need the normality? I want to repeat the argument we did for the sigma z. I want to decompose with respect to the spectrum of B. I can do that. I just need to use spectral theory appropriately. And this thing looks a little bit ill-defined, but you can make it well defined with sort of respect to the spectral measure of B. This is sort of a non-commutative spectral measure with two arguments. It captures all the non-commutative behavior of B and A. Please. Did I pass it? Yes. Go quickly. It captures all the non-commutative behavior of A and B, and the calculation remains the same. You get this e to the, well, you would get an e to the lambda A star, e to the mu A star. You commute to the other sides. You will get this factor coming out, and the rest of this factor, that is the scaling problem. And now if you look at this function closely, then this prefactor, it is something which can exactly, it is exactly 1 if lambda equals mu, and it is completely, it goes to 0 if this goes to infinity in any other case, because the real part will be smaller than. The only way the real part of this can be 1 is if these two agree, and otherwise you have something which will go to 0 after rescaling. I forgot the after rescaling. I mean, essentially, sort of with rescaling, this goes to delta lambda mu. Okay, so sort of you have to look on the diagonal. Okay, and that gives us a construction for arbitrary generalized spin boson models of a ultraviolet renormalized supercritical model. We do this. You can take an arbitrary. Yeah, I mean, okay, I mean, it heavily depends on your spectral measure. But I mean, you can in principle integrate the characteristic function of the set lambda. So this is really the characteristic function of the set lambda equals. You can integrate. That will either be the, if it's a 0 set, if you don't have atoms there, then you will have a 0 as the value, but sort of, as we saw before, sort of we're on the, that was exactly, we had a 0 set for lambda equals mu. That's why the integral became 0. But of course, I can write down a measure which belongs to an operator, which this is non-trivial, in which something comes out. And something comes out in a way that we can really not go into a decoupled model. That it's because of, we have exchanged these two sides, and this exchange of lambda and mu, that in a non-commutative setting for A and B cannot be reversed. You cannot just sort of decouple, exchange lambda and mu. I actually tried when we wrote up the paper, and it just doesn't work. It's really heavily coupled. But the construction is exactly the same as before. You have sort of this new scalar product on this subspace of Fock space. You make it to a Hilbert space, and your dressing or this scalar product element will again give you sort of a nice embedding into the original space, even though CCR are changed there. This expression can actually, using simple measure theory, be proven to yield a unique bounded symmetric quadratic form. So there's a bounded operator, AJB, for the dressed spin, dressed free particle, whatever. And you get a renormalization scheme result, which yields exactly the operator consisting of this dressed spin and sort of this drawn back onto FGB free. Definitely non-trivial coupled spin boson model, or a generalized spin boson. Okay, so what have we done? We have constructed fully interacting generalized boson models, and in the last part, I'm sure it's fully interacting from the Hamiltonian side. For the spin boson model, there's definitely work to do, and that directly relates to studying the spectral and scattering theory of these models. And so sort of that's definitely work that needs to be done to sort of see what exactly the behavior of this model is. And of course, I mean, as I showed in the motivation, this is not the only supercritical model. The next canonical model with a linear interaction is the relativistic Nelson model, to sort of try to incorporate this type of dressing in an appropriate gross way. Okay, yes. Yeah, I'm finished in a sec. Okay, then we can also direct. Yes. Mm. But that might correspond to us taking this this rescaling of the mass. So we take the regularized mass and we rescale with sort of a diverging mass term. So maybe that is exactly sort of a renormalized. Oh, no, that this would be. Yes. We can directly continue the discussion because I only wanted to thank you for your attention and congratulate Volker again to his project. No, I mean, what I propose is an analytic. So it's sort of a method for analytic organization, and the Alemania part was sort of motivation why it's a good method. What do you mean with BPHC? Yeah, but that's for quadratic models. Yes, you'll need a quadratic interaction to do Bogor-Yubov. Nelson, you'll have this linear, so you only have e to the field, nothing. But yeah, I mean, this is, I mean, it's similar, but for linear models. So I mean, you would actually, if you look at the paper of Ginipre and Belo, what they do is they do sort of this type of dressing with quadratic exponent for a quadratic model, and then they relate it to exactly what you say, a Bogor-Yubov transformation, so that you can sort of. They actually, the essential self-adjointness we can prove directly, they prove using Bogor-Yubov. That might be them. Mhm. Mhm. Not yet. Probably, I would assume that that is very dual to Ginipre and Belo. Models exactly solvable in that way, then it's probably dual to. Maybe the models are more general, but sort of the method, they are correspondence. But no, we haven't. We really sort of, we are still at the level of linear. I mean, this is work initiated. I wanted to say that, but forgot it. Actually initiated when I gave a talk in Milan on ultraviolet normalization using Feynman-Katz formats. I said, I would like to do relativistic Nelson in 3 dimensions, but I don't know how all the expressions I get convergent. And then Marco said, let's try this type, and that's what happened.
Then we have 5 minutes. You can get coffee. Coffee should be ready. I